Section 4.5 is really vaguely called other applications. So I'm going to leave a couple of them for you to figure out, but there's a couple that are weird enough that I thought we should do some examples in a video. The first is this example where you have a rectangular box and we are going to deal with the surface area of the box. So this box has top and bottom are squares, and the overall volume is held fixed, 250 cubic centimeters. The material for the top and the bottom costs, so the two squares cost $2 per square centimeter, and the sides is half that, $1 per square centimeter. So we're supposed to find the dimensions that will give us a minimum cost for the materials. So hopefully that tingles your little spidey senses and you think, oh, I'm going to minimize some function. In other words, you're going to find the derivative of some function and set it equal to 0. All right, so first of all, you should always write what your variables are representing. Okay, I know it seems like an extra step, but it's important, especially at the end when they ask you for some other thing that you're not expecting. All right, so x is going to be the length of an edge along the square bottom, and then y will be the height. So your volume is x squared times y, right? Because it's just all three of the things being multiplied. And that's volume is being held static, as I said, at 250 centimeters cubed. Then we just have to figure out the formula for the surface area. And in fact, we don't want just the equation or the formula for the surface area. We want the equation of the cost of the materials of the box. So we've got the areas of the faces of each box. That's how you add up the faces, the area faces, and you get surface area. But specifically, the top and the bottom are $2 and the sides are $1. So you've got $2 times the x squared plus $2 times x squared, so that's the top and the bottom, okay, plus $1 times 4xy, and that's each of those four sides. So this is a cost function, and it's based on, the variable is just the length of an edge along the square bottom, and you know that because you wrote it all out nicely. All right, simplifying, we get 4x squared plus 4xy. And again, that's a cost function, and we want to minimize the cost. So they solved for y. Oh, for the volume. Okay, so that other equation had x squared y equals 250. We got an equation in terms of x. So here again is x is our variable for y, and now you can substitute that into the cost function. And now you can see that this cost function is only in terms of x. There's no other variables in there. Now we can find the derivative of it. And to set that up, if we write this second term 1000 over x is 1000x to the negative 1, it's much easier to differentiate. So c prime is 8x minus 1000x to the negative 2 power. All right, we set that equal to 0 to get our critical value. And that comes out to 125. So, oh, I'm sorry, x cubed is 125. So x is 5. So that makes much more sense. So those sides along the square bottoms are 5 by 5. And then to figure out what the height is, you can use that volume equation, and we get 10 centimeters. And so your dimensions of your box are 5 by 5 by 10. And then if you wanted to figure out the cost of the materials for the box, you could just plug in that 5 for the x value and figure out that the cost of the box is $300. The other homework problem that I had trouble with in this set was the oil pipeline question, and I've seen it before, and somehow every time it gets me. So let's go over it. So in this case, it's really hard to see without the picture, but take a minute to read it. They're going to lay some oil pipe, and some of it has to go underwater and some of it has to go over land, and it's much more expensive underwater than it is over land. So then you have to figure out how far it goes underwater and how far it goes over land. So let's look at the picture. Okay, so this length of pipe right here is the pipe that goes underwater. And then of course this pipe right here goes over land. And so this corner right here can be anywhere along here. In other words, you could go straight from the oil rig to the storage tank directly, but that's going to be all underwater pipe. So, but you can see obviously that if you go through the water the shortest distance, then you still have a whole long way to go over land. So there's a point here somewhere where it minimizes the cost of the pipe. All right. So the way you set this up is just like this picture. It's a 3 mile offshore, so it's the rig to the shore is 3 miles directly. Okay, so if you went the shortest amount of water pipe, you would go straight 3 miles, and then from point A to the storage tank is 8 miles. Now P is that variable right here. Okay, it's just this little bit of red right here. So if P is 8, then you go straight from the oil rig to B, the storage tank, right? If P is 0, then you go straight to the beach, that 3 miles underwater, and then this 8 miles along the shore. All right, so we just have to write an equation for that. So X is the distance from A to P, okay? So AB is 8, so PB is 8 minus X, right? Because the sum of this little bit right here and the shore pipe is 8. So 8 minus X plus X equals 8. All right, and then we get to play with our old friend Pythagoras. RP, which is the hypotenuse, right, of this right triangle right here, is equal to the square root of x squared plus 9. Okay, so the length of underwater pipeline, or underwater pipe, is the square root of x squared plus 9. And then, therefore, the total cost of the pipe is 800 for the water pipe, which sounds like a bong, sorry, 800 for the pipe underwater, times the square root of x squared plus 9, plus 400 for the land pipe, which is 8 minus x is its length, and 400 is the cost per foot, or whatever it is, miles, I don't know. All right, so then just making that radical into a rational exponent, and then distributing that 400, you've got that. And of course we want to find the derivative of that cost function, because we're going to set it to 0, and that'll be our minimum cost. All right, so that's differentiated. Hopefully that's not too much of a stretch. And then rewriting this rational exponent back as a radical, then we can see that this is our first derivative of our cost function. Now they're making a note here that the second derivative of the cost function is this number, which I believe is always positive. In other words, it's concave up, which means that a critical point set equal to 0 will be a minimum by the second derivative test that we already learned. All right, so we set it equal to 0, the first derivative equal to 0, and yada yada yada, mathy, and we get x is plus or minus the square root of 3. So obviously the negative distance right there doesn't mean anything for this particular situation, so we're just looking at positive root 3. Okay, so again, the second derivative, if you plug in that critical value, gives you a positive value. So we know that it's concave up there. In fact, we know it's concave up everywhere, and so we know that at that critical value, x equals root 3, we have a minimum value, which is what we're looking for. So the minimum cost is incurred if point P is located square root of 3 miles along the shoreline from point A. Okay. Oh, that's nice. We should check the endpoints x equals 0 and 8. So those are those extremes where you go straight to the shore or straight to the storage tank, just to make sure that it's not getting that those aren't absolute minima. So at c equals 0, it costs $5,600, and at c equals 8, it's $6,835, and then our answer of root 3 gives us a cost of 5,278 approximately. So that is indeed the minimum cost. Very thorough of them.